Hey guys, welcome back. This should just be a quick video. It's intended to go along with our evidence of evolution video, just to support one of the ideas in that video with a little bit more information in case this is something that you haven't covered before, perhaps in other classes, or you just needed, a different approach or different perspective on how it works. And that is radioactive dating. And so we can use radioactive isotopes of certain elements to provide a dating mechanism for stuff that we want to figure out how old it is. One of the most common of these isotopes is carbon-14. And so carbon-14 has too many neutrons. Most carbons have 6 neutrons to go along with the 6 protons that carbon has. So these radioactive isotopes are just that, versions of elements that have a little bit too many neutrons. Now, the normal version of the element is more comfortable for the element, right? It's a little bit more energetically stable. And so these radioactive versions will move towards being the normal version by randomly and occasionally ejecting the extra neutrons, right? To get them out. Go away, extra neutrons. The key point of what I just said, the important part there is that it's random. When they do it is a completely random thing. When they get the chance, they randomly shoot it out. Bye. And then it goes down to being its appropriate level. Because it is random, it makes the rate of this decay, is the phrasing for it, exponential. So rather than being a linear rate, where say you lose 14 neutrons per 7 seconds, right? The rate of neutron loss in the entire population of this element depends on the amount that you have. Right? And so if you're flipping coins, for instance, right? If I have 1,000 coins, I can expect to flip more heads than if I have 100 coins. Right? The rate will still be 50-50, but the 100 coins should only produce around 50 heads, right? Whereas the 1,000 coins should produce about 500. And what this does is it gives us a half-life for these radioactive elements. Yeah? And so if I start with a certain amount, after a given set amount of time, through statistical probability, I've lost half of how many of those isotopes I had. Right? And so if I started with 100 isotopes, after the half-life time, I'm down to 50 isotopes. Okay? After that same amount of half-life time, I'm down to 25 isotopes. After that same amount of half-life time, I'm down to 12 and a half isotopes. Right? So it's either going to be 12 or 13, right? Somewhere in there. And so these half-lives of these isotopes allow us to give dates to things, right? So if I told you that I drink half of my milk every one day, right? If I start with 500 gallons of milk, right? On day 2, right, I'd have 250 gallons of milk left. If you walked into my refrigerator and found that I had 50 gallons of milk left, and I start with 500, you could do the math to figure out how many days have gone by. Right? If you imagine that in your head, right? I start with 500. Every day I drink half of what's left, right? And you open the fridge and you find 50, right? You could use that math to figure out how many days have passed. We do the same thing with this radioactive isotope dating. It's just instead of days, we use it to measure millions of years. Right? So it's really useful for if we dig up a fossil of maybe like a tree. Right? If that tree was alive 100 million years ago, right, it's going to have a certain amount of carbon-14 left. Right? And so there would have been the base level, okay, and it would have gone down by half and gone down by half and gone down by half and gone down by half, okay, every given amount of years. And I can use that math to figure out how many half-lives have I gone through. Right? I have an established half-life X times how many half-lives I've gone through equals how many years have gone by. Yeah. And so that's how radioactive dating works. Important concept, not super confusing. Cool. That's it. Bye.